Okay, I've started. What I was explaining
All
to
right.
you, right? We're able to solve this thing up to this point where we're supposed to substitute only for z, right?
Yes, sir.
Where we're supposed to substitute only for z. So you can see that the
Sir,
whole
I'm
of
not
this.
seeing the screen, sir.
Ooh, you
I'm
cannot see
not
the
seeing.
screen.
Yes, sir.
Okay, let me see. Somebody is there. I told you that you should not allow anybody to make mistake. Can you see the screen now?
Yes, sir. Okay.
So I was saying that we solved this thing up to this point where we arrive at where we're supposed to substitute for z. Okay, and what were we looking
Yes,
for?
sir.
We're looking for this hypergeometric function. Okay, for the
Yes,
case
sir.
where it is negative here, all this one, two, and the rest, you can be able to brush it, right? Because they are we already solved all these things. And when we talk about the Poch hammer symbol, you know what it is and how to go about everything, right? Up to this point, right?
Y- Yes, sir.
So now, this is my explanation how we're able to get from the left to the right hand side. So now this is where we stop. Are you there?
Yes, sir.
Now we're now in this place. We're supposed to put negative x here, right?
Yes.
So if we go to the next point, it's supposed to be plus, which are accepted, plus negative x, right? So are
Yes,
you?
sir.
Then this place is supposed to be negative x. So if you do that, we're going to get 1. This plus and negative will give you negative x, right?
Yes, sir.
Yeah. So now this and this they are the same. For example, I showed you here that the logarithmic function is odd. So for odd logarithmic function, this is equal to this. This side for odd logarithmic function, this 1 minus x is always equal to minus 1 plus x. You get it? I need your yes. You get it? Hello?
Yes. Yes, sir.
Uh-huh.
Yes, sir.
So because of this is always equal to this, because the function is odd, then the negative comes out. So that's why when this one now cancel with this, we now arrive at this point.
Okay.
So it's clear now.
Yes, sir.
So it's because the function is odd. So we can now rewrite all this. So now I just put this one just to bring your brain back. If I ask you to compute this is just equal to what? This, right?
Yes, sir.
Then we have already shown all this. We can show that you can prove by induction that this is equal to this, right?
Yes, sir.
Perfect. And then we can evaluate this because I've already done this with you too.
Yes, sir.
So for you to evaluate this, what are you going to use? You're going to look for what? N is equal to 4, right? There n is equal to
Yes.
4. So and then we get this. We already did that, so I'm just trying to refresh your memory. All these
Yes, sir.
are done. So this is where we're supposed to start today. So what I want you to do is the good news is that I'm making you to be very strong. The people that are taking this course, they have not gone so deep like you, because the last time you made me to know that you took this program and you are very intelligent. So I like dealing with people who are very intelligent. If you were weak, I would have said no, this one a weak person. But since you are very bright and you want to do this, and maybe you want to do your masters, right?
Yes, sir.
So when you know this now, when you go in for your masters, it will be very easy and so on and so forth. So that's why I went to this level again, so that you understand, because this is math method in physics, mathematical method to use in physics.
Yes, sir.
So we're going to look at Legendre and Bezier function, and these Legendre and Bezier function are very, very important. We call them special function in math physics. Why? Because we always come across them, and they always arise in solution of differential equation in physics. So we have a lot of differential equation either in physics, we have them as differential equation in engineering and applied mathematics. So this is how they appear. Are you with me? Are you with me? Joseph, are you with me? Hello? Hello?
Hello, sir.
Are you with me? Are you with me?
Yes, sir. Yes, sir.
Ah,
Yes, sir. Yes, sir.
okay. Can you hear me?
Yes, sir.
So this Legendre function, a function, they appear as solution to this equation. This equation is referred to as Legendre differential equation. Do you get me?
Yes, sir.
So this equation, so far you get an equation, you are able to isolate it in this form. One, two, and you get these points. Then you will say this is an example of Legendre equation. So when you get this type of equation, then the solution is just very simple. Okay, we have the
Okay.
first Legendre
Yes, sir.
polynomials. So the solution is what we're going to look for this type of solution. So anytime you solve, you appear and you get something like this, then is we apply the Legendre solution. Okay,
Okay. Yes, sir.
so the Legendre function appear as a solution to what Legendre's differential equation. Now the
Equation.
first thing
Yes, sir.
before you head, it's what you should know how to solve this problem is Legendre polynomials. This one, when you see this, they represent Legendre polynomials. They are polynomials, right?
Okay, sir.
So the solution for the integer values of n, the solution for this, if you say p1, these are the solution. P0, where n is equal to 0 of x. Then we have the situation where n is equal to 1. We're going to have p of 1 of f of x. Eh? Then we'll have
Yes, sir.
when n is equal to 2, then we're going to have p of 2 of f of x, I mean of x, right? All
Yes,
these
sir.
values, this like this, they are called Legendre polynomials. And then they have their various solutions. This one it will be equal to a certain value. Let's say 1. This one can be equal to a certain value x squared. Okay. So you say
Yes,
the
sir.
solution for integers, the integers are n, where n is 1, are called Legendre polynomials. So they these polynomials are somehow orthogonal over this interval from -1 to 1. That means they oscillate between -1 to 1. And they have a weighting factor, or a weighting function, or a weight function of 1. So they start from where? -1 to 1. This is the polynomial p of this, and another polynomial p of this, which are just like this, right? Gx.
Yes, sir.
When you do that, you will get this. Now, in this situation, m is not equal to n. Okay?
Yes, sir.
We're going to see, you have to keep this at the back of your mind. Now, the forceful polynomials, as I said, when n is equal to 0, is 1. When n is equal to 1, it is x. When n is equal to 2, this is the solution. Okay?
Yes, sir.
Thank God you are with me. Now, the general function, how to get whether n is equal to 1, n is equal to 2, n is equal to 3, is given in this form. Keep this one at the back of your mind because we're going to use it.
Okay, sir.
Uh-huh. Now, let me finish with, I'll finish with Legendre polynomial, and I know you have a certain small idea for now. Don't worry. By the time we solve a big problem, then you understand whether you understand it or not. We'll solve some problems so that you get to know what is it, right?
Yes, sir.
Yeah. Just give me 1 second, please. I want to check something. Okay. Now, if you look at this, are you with me?
Yes, sir.
If you look at this one now, it is called associated Legendre function. Have you seen?
Yes, sir.
Okay.
Hello,
Now,
sir.
yes, are you with me? Now, the difference between this and the other one is just this point here. Eh? Hello?
Yes, sir. I'm with you, sir.
Uh-huh. So
Yes, I'm with you, sir.
if you check this and the Legendre polynomial, check the Legendre polynomial, everything here,
Sir,
1 minus.
it's not showing on the screen, sir.
Hi, God. What is the problem with this thing now? Is it showing now?
No, sir. Yes, sir. Yes.
Are you seeing my screen?
Yes, sir.
So I was saying that the difference between this one is called associated Legendre function. If I say write down the formula for associated Legendre function and compare with the formula for Legendre function, the difference is just this. See, this one is 1 minus s squared minus 2x. Forget about this one. This one is d square y by the x square, dy by the x, and there's that one. You can always keep it at the back of your mind, right?
Yes, yes, sir.
So just check, look at this point, n into n plus 1. Then if you check this one, you
Yes.
see everything is almost the same. The only additional one is this point.
Yes.
Yeah, so the only additional.
The additional one is minus m squared over 1 minus s squared.
Correct. Are you with me?
Yes, sir.
Just 1 minute.
Sir, I'm with you, sir.
Okay, thank God. I'm talking to myself.
Okay, sir.
Okay, now let's go ahead. So now in this associated, it also have its own associated function. Remember the other one was only p of n x, but this one now, because it's associated, it has p of n and m, right? Because if you see now, the associated here, you have n here and you have m here. Okay,
Yes, sir.
Benny. So
Hello, sir.
okay, now this is
Yes, sir.
now let's see how we can. We have spoken about Legendre. We have spoken about associated Legendre. Now we have also spoken about. Let's talk about Bezier function now. You can see all the function. The Bezier function also is also a solution for Bezier differential equation. So I can give you plenty equation. All you need to do is, how can you make it to look like a Bezier differential equation? How can I make it to look? Are you with me?
I'm with you, sir.
And how can you make it to look like a Bezier a differential equation? How can you ever make it to look like Legendre differential equation. How can you identify it to look like associated Legendre equation, right? So the
Yes,
only
sir.
key point there is the other one. You realize that it was different something. The coefficient for Legendre is what? 1 minus x squared. So
Yes,
if
sir.
it's 1 minus x squared, then you start to be talking about Legendre. Then this one will be minus 2x.
Legendre. Yes, sir.
It should minus 2x.
Yes, yes,
This one will be minus
yes,
2x.
yes. Minus 2x. Yes, sir.
Then this one will be n into what?
Yes. N into n bracket.
Uh-huh.
Yes.
Is it correct?
Yes, sir.
Uh-huh.
Why?
Uh-huh. So then why? Then we'll be talking about Legendre. But for Bezier, you now realize that is we don't need that. Bezier is also unique in its own form, right?
Yes, sir.
Correct. So this one now is Bezier differential equation. And then the solution, the Bezier function, we have two kind. We have this one. This is the Bezier function, which is also the solution for the Bezier differential equation. Is given in this form. Okay?
Yes, sir.
And then is given in this form. So this form is very important. The most important thing, are you with me?
Yes, sir.
You can see that the n is here and then the n is here. Only two places n appear. And then we have the n here again. Are you with me?
Yes.
What you should note here is that this thing, j of n of x is equal to, I call it yama 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 yama. What is important here is x all over 2.
Okay.
Eh?
Yes, sir.
2k plus n. This point is very, very important. Why? Because this j is a function of x. So whatever value you see here, let's just say, for example, I say j of n, give me the value where x is equal to 4.
Mhm. Okay.
You will see that there is no x anywhere. So that's why I say all these places now will be yama yama. Then this one will be what? 4 by 2.
4/2.
Uh-huh.
2k plus
Uh-huh.
n.
Uh-huh. So you will see that that is the only place where x appears. Have you seen that? So this will
Yes,
give
sir.
you, this will be like 2, 2k plus n, right?
Yes, sir.
Correct. But this thing I call yama 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 yama, this point here, you see k starts from what? K starts from 0, right? 1,
Yes, sir.
it goes to 2,
Mm-hmm.
goes to 3, up to infinity, right?
N. Yes.
So what we're saying is that this first term you are seeing here is just talking about sign changes. For example, minus 1, when n is 0, this will give you 1.
Okay.
Minus 1, when n is 1, when n is 1, this will give you minus 1. So you see it's 1, minus 1, it will be 1 again, it will be minus 1, it will keep
Mm.
alternating, right? Because when the power
Yes,
is
sir.
odd, it will give you minus. When the power is even, it will give you plus. So you see that this thing is only talking about alternation. Remember, I said this thing moves between the integral we're talking is the integral is changing between what? Minus 1 to 1.
-1 and 1.
Correct. So that is what is happening. So this thing is changing between 1 and minus 1 or minus 1 and 1. That is the essence of this upper part. Exactly.
Yes, sir.
Then this second part now is factorial, right?
Yes, sir.
So this is gamma. So we're going to look how we're going to. So this equation is very easy to memorize. It's not difficult for you to put in your mind. It's not difficult. Just k factorial. Then this one is gamma function, and then this one you say this one is the sign. This is the only point that is important. So you can always find your way out. with this equation. You can always write it. If for example, I ask you, write the first kind function for Bezier. Write the first kind Bezier function. This is what I'm asking you to write. Hence, solve a particular problem. We're going to see how to solve a problem, right? Then this is the Bezier function for the second kind. The first kind is given by J. The second kind is given by capital Y. I'm not going to give you the expression for this now because it's bigger for your level. This is a math method 300 level. When you come to 400 level, we'll brush this one. Is that okay?
Yes, sir.
But we're going to see how to use it very soon. When the time reach, I will tell you what to do with it. Now, this is the first problem I want you to look at. I've spoken about Bezier function too much, right? I mean, Legendre. Sorry, I would have asked you if you are able to identify. What type of equation is this?
This is Bezier.
No.
This is J and X.
Look at it.
This is Bezier.
This cannot
Okay,
be
no, the
Bezier.
first one up that is said verify P2 open bracket. Okay.
What? No, listen, I say,
Yes,
what type?
this is okay. This is legend.
Thank you. This is Legendre. This
Yes,
is
sir.
this is Legendre. Hmm?
Yes, sir. Yes.
Okay. Now the question is, prove that P2 will satisfy this equation. You know that we have P0 satisfy this equation. How? If you put P0, the left hand side will be equal to the right. I mean, the left hand side will be equal to 0, the right hand side will be equal to 0. If you put P1, let's say P0, let me go back. This is P0. Have you seen?
Yes. Yes, sir.
If you put it, it will satisfy. The left hand side will be equal to the right hand side. If you put P1, it will also satisfy. The question now is prove that P2, which is equal to this, also will satisfy. The left hand side will 0, the right hand side will be 0. That's what we're talking about. So let's go back. So if you take for the first one, P1, I mean P0 is equal to what? 1, right?
Yes, sir.
So what I was saying is that if you put 1, you are going to get 0 everywhere here. How? How to do it is that, are you with me?
Yes, sir. I'm with you, sir.
You're going to differentiate. Anytime you differentiate this, for example, you're going to differentiate. How to do this is like d square p of x of 0 x by dx square. That is it. Then they say 1 minus x square. Then this will be minus 2x, right?
Yes, sir.
This one will also be d of p of 0 x all over.
Yes.
Then this will say plus, in this case, we're saying n is equal to 0. So this side already give you 0. Then this also will be 0. N is equal to 0. So this one now, this is just saying that
Yes,
1
sir.
minus x squared. Then you say d square, sorry, d square of 1. Anytime you differentiate
Yes.
constant, is it not going to be 0?
Yes, sir.
So you realize that because this one is a constant, this one is a constant, then you realize that this guy will give you 0, this guy will give you 0, this guy will give you 0. So you realize that the left hand side is 0 and is equal to the right hand side, which is 0. It therefore implies that the first polynomial satisfy the differential equation. If we do the same for the second one we're saying that p of 1 of x is equal to x. Is it x to x squared?
Sir, it's not showing on the screen again, sir.
Oh, when something is about to go like this, we say it's not showing. Are you not seeing my screen?
I'm not seeing it, sir. I'm seeing it, sir.
You are seeing it now.
Yes, sir. Sir, please, sir, if you want to send the slide to me, please, those places where we work, don't raise it. Oh.
See me, I've already erased it because you're not seeing. Okay.
Oh,
Okay. Now let me do this one so that you quickly get it. Now
okay, sir.
check this now. Check this polynomial. They say for the p of 1 is equal to 0. Here we're saying that n is equal to what? 1. Okay. Then
Yes, sir.
p of 1 of x is equal to x.
Mm.
So let's go and check it here. Let's prove using this polynomial to show that p of 1. So p of 1, we're not saying 1 minus x square. Then this will be d square of x. Why? You know where x is coming from?
Yes, sir.
Eh?
No, sir.
Okay, if you don't know, let me take it one step at a time. Okay. Now this will be d. Anytime I ask you, there will be p of 1 of x,
Yes,
then d what?
yes,
D of
sir.
x square minus 2x, right? D of p of 1 of x by dx, right?
Yes, sir. Yes, sir.
Plus, remember we're saying n is equal to 1. So we have 1 into 1 plus 1
Mm.
y
Okay.
is equal to 0. So we're saying that for this thing to be okay, this side must be equal to 0. This side, left hand side must be equal to 0, just like the line right hand side. So now we know that p1 of x is equal to what?
It's equals to S.
Is equal to x. That's why,
X.
yes. That's why I was saying that I want to rush. So now we have this. We have d square of x by the x square minus 2 of x. In this case, we're not going to have y has changed to p1. So this place is supposed to be y. You see, everywhere we put it was p1, p. So because this one is equal to y, right?
Yes, sir.
So this one was supposed to give you, instead of putting x here, it's supposed to be y here. Because this is that, right? You must follow me. So this now become d of x by dx plus 2x, right?
Yes, sir.
Is it equal to 0? That's
Mm.
the question. Now, this one, if you differentiate the first time here, if you get d by dx by
Yes.
x, then this is the first differential,
Sir.
then this is the
Sir.
x. Correct? Yeah? Talk.
Okay. That's what I wanted to say.
So this
It has
one,
been corrected. Yes, sir.
will give you what? This one inside here will give you 1, right?
Yes, sir.
So this
Yes,
one
sir.
will give you, so we're going to have d1 by dx. This one will give you what?
Yes.
This will give you 0 because
Yes.
you're differentiating a constant. So this whole place now will become 0, right? Then this one now will give you what?
0.
Dx by
Yes.
this will give you 1. So the only two will have here minus 2x plus 2x, right? You see that
Yes, sir.
the left hand side, this one is 0, is equal to 0. So this one too is also a solution. right?
Yes, sir.
Now the question now is, show that this one now we've done for zero, we've done for one. Show that this one too is equal to, it satisfies the Legendre equation. Okay. So
Yes,
for
sir.
us to show it is the same thing we just did now. So for this case now, n is equal to 2, right?
Yes.
They are also going to do just like we did. P of 2 of x. So everything is the same, right?
Yes.
So now what do? We will not substitute, we will not put everywhere we see this P of 2, we will not put this. So we'll put it here, we'll put it here, and keep going on.
Sir,
So
please, I can't see the screen, sir.
if I go out coming, you will not see this thing again. Oh. This is my write up.
No, sir, don't.
Are you seeing now?
Yes, sir. Yes.
Okay, don't worry. So please be writing as I'm going. If you are seeing, be writing. But the good news is I'm recording, whether I will be able to send to you. But I'm going very gradually.
Okay, sir.
So step one, I will put it very easy. Step one, this is the function that we want to do. Now, we now said this is, we want to express whether it satisfies the Legendre equation, right? This is the Legendre equation. So we want to make sure that the
Yes.
left-hand side is 0 and the right-hand side is 0. So this is the P of 2. So the first thing we'll do is we're going to do like this, right? We're going to change
Mm.
y to be equal to P of 2, right? Then we'll now substitute P of 2
Yes.
throughout, right? When we substitute P of
Yes.
2 throughout, we're going to get, let's first of all, for the first differentiation, we have to differentiate because we are talking about differentiation here, we are talking about differentiation here. So the first differentiation will give you 3x. Now we'll do the second differentiation, which is this by this. If you do the first one, you get 3x. The second one will just give you 3, right?
Mm.
Eh?
Sir, I don't understand.
The differentiation now, when you differentiate this one with respect to x, when you want to
Okay.
differentiate this now, you copy this,
Okay.
you differentiate this now. This will give you
Okay. Yes. 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 I'm
uh
with you now.
the second differentiation.
Yes, it will be 6. Yes, I understand now.
The second one now will be 3,
Yes.
right?
Yes.
If you differentiate this again, you get 3x.
Yes.
So what we have done
If you
is,
differentiate the 3, yes, it will give you 3. Yes, sir.
uh so this one now is this part. This one now is this part. So we're going to substitute. And then this one now is this part. So let's substitute. So if now we're going to substitute our solution into the Legendre equation. Okay, so when we substitute, we
Yes,
realize
sir.
that this part here is 3. See it here, right?
Yes, sir.
Sorry. Then this is minus 2. This one now, what is this value? 3x. Eh?
Yes.
We'll put it here.
Yes, sir.
Then this is 6. This is 2. Let me be showing so that you'll be seeing. This is 2 into 3. So 2 times 3 is 6. That's why we have 6 here, right?
Yes, sir.
So P2 now is the whole of this value. So we'll put the P2 here. Then when we open this, but before we open, we'll do it term by term. This term here, this first term, that is what gives you. So we take this times this 3 minus 3x squared. We see 3 minus 3x squared, right? This term, right? First term.
Yes, sir. Yes, sir.
The second term will this. The second term is this, which is minus 6. And then the third term is this long one here. And this one will just do this. This and this will give you 3. So it'll be 3 of this, which when you open, you will get this. So we have first term, second term, and third term. So we have to add all of them together. So when you add all of them
Okay.
together, okay, realize that
Yes, sir.
it will get 3 minus 3. We'll just get something of this nature. And when you add them together, it will become 0. So therefore, this P2 satisfies this equation.
Okay.
Yeah. So if you add all these things together, you're going to get 0. Right? That's what we're saying.
Yes, sir.
So if you put this one, put it here, take this one, put it here, take this place, put it here, and add all this together, you're going to get 0. So that is why you can see everything here. So for here, we're taking the first one with that. You take this 3 minus this 3, the one that has only with that x. This 3 and this one will give you 0. Then the one with x squared. You take this minus this will give you minus 9, plus this will give you 9. So this all this will give you 0, right?
Yes, sir.
That's what you see. Terms that does not contain x square, it gives you 0. Terms that contain x square is this, and this. It gives you 0. Since all the 10 cancel out, we have 0 equal to 0. So this also P2 satisfy the Legendre equation. Is that clear?
Yes, sir.
Okay. So the next question is find P3. For you to find P3, like I gave you P1, P2. I gave you P0, P1, P2, right?
Yes, sir.
How do we find this value? How do we find P1? How do we find P2? How do we find P3? How did I know that P1, P2, P1 is X, P0 is 1, P2 is 1 all over 2 into what? How did I know that? Yeah, 1 all over 2 into 3x squared minus 1. How did I get all this? For you to do that, we must use the formula referred to as Rodrigues formula. Rodrigues formula. So find P3 using Rodrigues formula. This is how Rodrigues formula is like. Understanding of Rodrigues formula. Rodrigues formula for rotated polynomial is always given by this. Is that clear?
Yes, sir.
And Rodrigues formula is a function of n only. So if you have 0, this guy will become 1. Let's do it together so that we will see how 0, 1, 2, 3 comes about. So we're using Rodrigues formula, right? So if we put
Yes, sir.
0, it means 0 of x. This will be equal to, using Rodrigues formula, it will be 1 divided by 2 to the power 0, 0 factorial, d cube by the x cube into what? X square minus 1, all these to the power 0. Shegbo?
Sir. Okay.
Is that okay?
Okay. Yes, sir. I'm with you
So
now.
sorry, I'm not supposed to put 3. So everything n is equal to 0. So this one was supposed to be 0. This one was supposed to be 0.
Mm-hmm.
Eh?
Yes.
So you can see that this 2 to the power 0 is 1. 0 factorial is 1. D to the power
Yes.
0 is 1. This to the power 0 is 1.
Is one.
Everything here is 1. So you realize
Is
that
one.
P of 0 of x is what? 1.
Is one.
Correct. If you do for P of 1, you get x. If you do for P of 2 of x, you will get 1 all over 2 into 3x cube, 3x to the power
Yes.
2
Yes. Four.
plus 1. So now the
Four.
question is find for P3. Let's find for P3, right?
Yes, sir.
So for us to find for P3, we're going to, anywhere we see n, we're going to put 3. So that is why we see when n is equal to 3, the formula becomes P, this will be 3, then this one will be 3, this will be 3, this will be 3, and everything will be 3, right?
Yes, sir.
And don't worry, I'm going to delete this because you already understand it. No need. Why? I need to write on that place. So now, for us to do it, well, first of all, this is the first thing to do. Are you with me?
Yes, sir.
You must first of all expand this. There are various ways to expand. This is to the 3 power. You can use 1 1, 1 2 1, 1 3 3 1, and so on and so forth, right? This is
Yes,
1
sir.
3 3 1 to expand this thing. So you know how to expand anything to the power n, right? You know how to do that. If
Yes,
you
sir.
don't know, yeah, but if you don't know, you go and learn how to do it. So first of all, we have to expand this. So the whole of this is going to give you this. right?
Yes, sir.
Eh, I hope you know how to expand this thing. You know how to do it. For example, if I say find x square minus 1 to the power 4, can you do that?
Yes, sir.
You can do it, right? You
Yes,
start
sir.
with 1. You start with, how would you do it? 1, 1, 2, 1, 1, 3, 3, 1,
3, 1,
1, 4,
4,
6,
6,
4, 1.
4,
What is this?
1.
These are the coefficients. So let's say, for example, it was 3. If it was 3, you see there is 1. Then the first thing that comes in, there is minus. It changes power. So minus come in. Then our first coefficient come in for 3. Then what happened? Are you with me?
Yes, sir. I'm with you, sir.
Uh-huh. So the first coefficient here is 1. The second coefficient here is 3. This 1. The second coefficient is 3. The third coefficient is 3. The fourth coefficient is 1. That is why this thing is being expanded. So you can do it, right? So this first
Yes,
one here is 1. Then it's 1 and this. It's like this 1. 1. This first value here, x. It start to reduce, right? X start to reduce. This is
yeah.
2 to the power 3, right? It will not start
Yes,
to
sir.
reduce. This will be minus what? 3 x to the power what? 2
Mm.
to the power 2 plus, you see, take this value, 3 x to the power 2, 1 minus, you arrive at this now, 1.
Yeah.
So can you do for this?
Yes, sir.
You can do it, right?
Yes, sir.
Okay, let me know waste time there. Are you attending this class alone or you're attending with somebody? Because like I see somebody is beside you there.
Yes, it's my husband that came in.
He's just watching us doing magic. Okay. Now you can see that the left hand side is equal to the right hand side, right? Now what we are going to do is
Yes,
we
sir.
are going to differentiate this thing at 3 times, because this equation is saying that differentiate it 3 times. So that is what we are going to
Mm.
do. So for us to differentiate the first time, we're going to get to differentiate this is 6 x to the power 5. So you differentiate the first time, you got this, right?
Yes.
You differentiate the second time, you now take the whole of this, differentiate the second time, you get this, right?
Yes.
Then you differentiate the third time. When you differentiate the third time, you will now get this, right?
Yes. Yes.
Then you now factorize. 24 is common. So if you take 24 times 5, you're going to get this. 24 times 3, you're going to get this. So now the third differential is this. So this is what we have seen. This value here. Are you there?
Yes, sir.
Is equal to this. So we're going to rewrite this Rodrigues formula. Instead of putting the whole of this, we're just going to put only 24. We're going to do that. So let's do it. So as I said, we now replace all that with the differentiation, right? The third differential. Have you seen?
Yes, sir.
Then let's calculate this. This 2 to the power 3 is 8. Then 3 factorial is just 3, 2, 1, which is 6. So this only this value down here will give you 48. So what is the final value?
Mm-hmm.
So when we simplify, we have 24 divided by this, which is 24 divided by 48. And at the end of the
Mm.
day, p cube, p third, the third one, now the third factorial, I mean a Legendre polynomial is equal to this. Now the next question I can ask you is that prove that this polynomial satisfy the Legendre equation. Can you do that? Yes, right?
Yes, sir.
Thank God you can do it. So Let's move to the next one. Now, this is another, I don't know. Let me not tell you what it is because if I say it now, what is this? Let me see whether you know it. What is this? J of n of x is what?
That is Brazil.
Thank you. Oh, you got it. Are you sure you are not opening your book? Oh, you got it. Okay. So that is Bezier what? Bezier function, right?
Yes, sir.
Uh-huh. I told you how to remember it. All this nyama you just keep it one side. Then this is the most important thing. Now, for n is equal to 0, this is how we get n is equal to 0. This is, you see, when I say compute this value, for you to compute this value, you have to first of all give me this, right?
Yes, sir.
So when you give me this, I say compute for n is equal to 0. Anywhere you see n, you put 0. So
Okay.
anywhere you see n, you put
Okay.
0. So if you come here, n is equal to 0. So this one just 2k. Yeah, n is equal to
Mm.
0. So you have k plus 1, right? And then
Yes.
yeah, there is no n. So now, what do we have here? We have k factorial. I'm talking about this denominator. K factorial
Okay.
into gamma of what? Now, you see, this one is 0,
Okay.
right? So we have gamma into gamma, I mean k plus 1, right?
Yes.
So what is this?
Yes.
This gamma of n plus 1 is equal to what? N factorial.
Yes.
We saw it, right?
Yes.
So
Yes.
the
Yes.
whole of this now will give you k factorial.
Yes.
So that is why we have k square, k factorial square. So you can see that for n is equal to 0, this value asked to compute is just equal to this. If you understand this, then you are very good. You will slap my exam with left hand. Do you understand it?
Yes, sir.
Yeah. I was supposed to teach a lot of you. Everybody, I had to tell the HOD that you should go so that I'll teach only people who have brain. People who don't have brain, I don't like teaching the math methods. So you have brain, Joseph. Are you with me?
Yes, sir.
You have brain.
Thank you, sir.
Okay, thank God. Let's go on. Expand the first few terms. When k is equal to 1, you know that what is this? This is a summation. This summation is saying that k start from 0, 1, 2, 3, 4, right? And when we say summation, it means that the first one k, when you get for k equal to 0, you say plus, for the case where k is equal to 1, plus k is 2, plus, and so on and so forth, right? So the question I ask you is that let's expand this thing within the first, not this one, no, this, within the first what? Two terms, or the first few terms. Are we together?
Yes, sir.
So now for the within the first few terms, we have already gotten the first one when j is equal to 0. Now when j is equal to 0, what is k? When we take k is equal to 0, because k is a something that is moving, we want to find the expression for this for the first two terms. Okay?
Okay.
When k is equal to 0, we can put k equal to 0 here. We put 0 factorial square, and this equal to 0. So this one is very simple. So we realize that both left and right hand side, 0 factorial is 1, 1 square is 1. Anything to the power 0 is
Yes.
1. So anything so you see this one
This
equal to
one.
1. So for the first
Yes.
case, when k is equal to 1, 0, we're going to get 1 plus. Now let's look where k is equal to 1. When k is equal to 1, the
One.
same thing
Okay.
happen. Okay, so when k is equal to 1, we're going to have minus x squared over 4. You understand, right? 1 factorial is 1.
Yes.
Mhm. And then, is that clear?
Yes, sir.
This one gives you the minus, which you see here. Now let's move to the next one. For k is equal to 2, for k is equal to 2, you do the same. 2 factorial and the rest, we're going to get this. For k is equal to 3, you do the same, you get this, right?
Okay.
Now let's do the summation. So the approximation, now the third step is we carry the approximate expression for x, summing the first few terms for this. The first one is 1, which is this. The second one is x squared all over this, right? The third one is this. The fourth one is this. Are you with me? So we are summing.
Yes, sir.
Eh?
Yes, I'm with you, sir.
Now, for very small value of x, we always approximate, because if x is equal to 1, this will become this will be approximately 0. It will be 1 divided by 6 by 64. If you take again 1 divided by 2,300, so it's approximately 0. So as you are going further away, this value is approximately is going towards 0. So when we say for small values of x, we can we can we can we can avoid this term. We can neglect this term. We can neglect higher values of higher powers of x at very low small x. We can do what? Neglect higher
Negative.
powers of x. So in that case, if I ask you to give me expression for this j0, okay, you just give me and say the answer is approximately this. Hence, if I say calculate j0 of 4, okay, what will be the answer?
Yes,
It
sir.
will be 1 plus 4 square divided by 4. Sorry, it's not plus, it's negative.
Negative.
Uh-huh. So this will give you 1. This will give you 1 minus 4 square is what? 16, right? So this will just give
Yes, sir.
you minus 4. This will just give you, what is the answer? Minus 3. That is the approximate value for j0 of 4. We'll use it if we go further. By the time you come for your math method 2, you know you do math method at 400 level again, right?
Yes, sir.
Uh-huh. You meet me, I will do all these higher values. For now, I'm just doing the lower ones. So this is the approximate. Okay. Now, final
Yes, sir.
answer is that for small j of 0, this is the answer. Okay. From here, we got
Yes, sir.
this. This is the formula. From there, we got this. Is that clear?
Yes, sir.
Then now I've done for j0. You can do for j1 now. I don't think I'll be there to show you. It's the same story. J0 for J1, you first of all put the formula, you put for J1, you get this. This is the only place where you're supposed to know. And then how do we move from here to here? You use this formula. When it is,
Sir, the screen is not.
I beg you, make the skin come out now. Are you with me?
Yes, sir.
Is it showing now?
Yes.
You always use this formula. When it is n plus 1, okay, this will give you n factorial, right?
Yes, sir.
What happened here? This from this to move to this side, this one must always cut out. So if I say give me for k plus 3,
Okay.
eh,
Yes, sir.
what will be this? This will be equal to k plus what? 2 factorial. Is that clear? If I say
Yes, sir.
gamma of k plus 2, this is automatically k
K plus 1
factorial.
factorial.
Who is there beside you to disturb you now? Your baby is disturbing you. So this is how you go about it. So that's why you see this guy here has changed. You must always change it in terms of factorial. So that's the only thing that you need to do. N is equal to 1, so you put 1, right? So we'll now start to do the magic. You put for k equal to 0, you put for k equal to 1, you put for k equal to 2, k equal to 3. So you put for k equal to 0, what do we get? K is equal to 0. This one will give you 0 factorial, this one will give you 1 factorial, 0 factorial, 1 factorial, everything here will be, and then you have, for k equal to 0, you have x over 2. For k equal to 1, you go ahead and do that. You get that? For k is equal to 2, you do your expression, you get this. For k is equal to, so our approximate here, let me delete this thing because it's, so our approximate for this case, when x is very, very small, the approximate expansion is this. You see that for 0 is different, for 1 is different. You can go ahead and do for 2, 3, 4. If I say do for 4, you would spend a whole, is for your PhD work, or you use computer, you use octave to do that. So our own approximate value here for very small is the first two terms, right? And this is it. So the expansion, final answer, the for J1, that is the result. I hope there's no question there. Joseph,
Sir, I'm with you, sir.
no question.
No, sir.
Thank you. Okay, let's move to this one. Now, this one is saying that show that this is equal to that, right? Now, this is what you should note. We have what is referred to as a property too. When it is even, we're saying that the j of negative is always equal to j of positive. But when it is odd, the j of negative, you have to remove the negative, then you put it just the way we did for the lane, or just the way we did for the logarithms, right? Remember we did that?
Yes, sir.
Correct. So prove this. Now, if I say show that this is equal to this, is a very simple step. Just make sure you put your j of n. When you put your j of n, then you substitute, instead of x, you put, make it to be minus. What is j of n? That is the second step. I decided to delete it because this place was getting full. You already know j of n, right?
Yes.
J of n of x. You know it, right?
Yes.
So when anywhere you see x, you put minus. That's the meaning of this. So when you do that, at the end of the day, you will see that this left hand side will be equal to this. Now, this is how you go about it. So anywhere you see this, you put. So when you do that, you realize that this, the only thing I told you, all this one has nothing to do with x. So this one will repeat the way it was. This is the only place you have minus because this is the only place where x is affected, right?
Yes, sir.
Mhm. Now, there is, since the exponent in the term, in each term, the exponent has this. We can separate it. We can separate the power. So we can separate this. So instead, you know that this one now is just like minus 1 times x over 2. You know
Okay.
that this is like this, right? So, and then we say
Yes,
2
sir.
has the power 2k plus n.
Mm.
So now this minus can take the whole of this power, and this one too can take the whole of this power. That's what we're saying. Okay,
Mm.
the minus take the whole of that power and that one, right?
Yes.
Correct. So in that case, we also know that this, no matter the value, because this is even, no matter the value of this, all this will always give you plus 1. So for example, when k is 0, this is 1. When k is 1, this is 1. This is plus. When k is 2, it is 4. When k is 3, it is 6. When k is 4, it is 8. So it is always, this will always give you even. It means that this whole thing here will always be what? Positive plus
Evil.
1. Okay? So we cannot, instead
Yes.
of writing 2k, we cannot change it to be what? We're talking with respect to this. So this whole thing here, instead for it to be 2k, we can just write it just like 1. Is that clear?
Yes, sir.
So in that case, we cannot simplify the whole of this. Let me delete what I want to do. Let me clean all this. So now, this one again, we have not touched anything here. The only thing we have brought here is this. how did we arrive at this? Check it out again. How did we arrive at this?
Sorry, sir, the screen is not showing.
Hi.
Okay, it's back.
Mm-hmm. You now know how we arrive at this, right? Ish. How we arrive at this. The value, this thing is supposed to be minus 1 all over 2k. Are you with me? I don't know why I'm writing this thing here.
Yes, sir.
So what this is saying is that um let me do it so that you understand very quick, then we move very quick. This is want to simplify, but what we're doing is that this is saying that minus 1 to the power 2k plus n, this is equal to minus 1 to the power 2k times minus 1, no, times 1, not minus, because um no, it's okay, minus 1 to the power n, right?
Yes, sir.
We have opened this power, so this is it. So this whole section here, we have simplified it to be 1, so it's just like 1 times, so 1 times minus 1 to the power n. That is why the whole of it disappear. I only have minus this. You see, it was like this, but now we have everything is only this now. Is that clear?
Yes. Yes.
Is that clear?
Yes, sir.
Mhm. Okay. So in that case, this is a key point now. So factor out this. If you bring out this, you carry the whole of this, you bring it out of this, right? Then everything we had before is just jn. Everything we have is just jn of x. Everything here we have here is just jn of x, right? Because you can see x, this is the only key point I showed you that time. Is it okay?
Yes, sir.
So you can see that since we factor out, this is that value. So we have already shown that this value is equal to this. It's very simple, right?
Yes, sir.
Mhm. This one is just for me to make you understand. If n is even, then this will give you 1. If n is odd, this will give you negative. Just for me to teach you, for you to just know
Yes.
the meaning of even and odd function. That is just for even, the minus will give you plus. For odd, the minus will come out. So our final answer is we have been able to show that this is equal to that, right?
Yes, sir.
Hermite and Legendre functions. I said I'm taking you to a little bit too deep. Is it entering your head?
Yes, sir.
Have you seen Hermite and Legendre function before?
No, sir.
You've never seen it.
Yes.
Just like polynomial, the Hermite polynomial are also the solution for the Hermite differential equation. And how you need to do, just like Legendre and the rest, Bezier, um, the Hermite function also have this kind of, you know, equation. So if you are able to identify this one, we can say this is y, right? If it is y, you can change it. So this thing has no meaning. It can be y, the square y by the x square minus 2x dy by the x plus 2ny is equal to this. But now this sign, this is showing this is the Hermite polynomial. These are Hermite polynomial, n of n, h of n, h of n, h of n. They also have their expression. The standard form from the Hermite polynomial can be expressed in this form. This one too is very easy to minimize to memorize, right? Where we have minus n to the power n. Are you with me?
I'm with you, sir.
Uh-huh. So with this one now, you can give me the Hermite expression for n is equal to 0. For n is equal to 0, what would be the Hermite expression? For what would be h? 0 of x.
It will be 0. Yes, this one will be 0.
This will be what?
This one has to be 0.
This will give you 1.
The first, yeah,
This will give you x square. Then this will now, you have to differentiate this. So this, the whole of this is 1. So this will give you e to the power minus x square. Now, when you have these two like this, it means that you add their power. Okay, so if you add their power,
yes,
it means that they will be 0. So the whole of this will just give you 1. So the Hamite for the first one is 1. Is that clear?
yes, sir.
Mm-hmm. Yeah, let's go ahead. I say you're following, and I'm happy. Okay, so this is also how the polynomial looks like. Have you seen it? The Legendre polynomial also satisfies this equation. This equation is the opposite, just like the opposite of Legendre polynomial. Legendre polynomial is 1 minus x. You start with a higher power, then you get to minus 2x, and then you get to all this. But this Legendre polynomial, it takes this form. So the expression for this is given by this. Let it not confuse you. By the time I touch one problem, you'll be able to understand it. Any question you want to ask?
So, yes, if there's questions, maybe when the material gets to me, that I sit down with it. So, if there's anyone that I don't really get very well,
You will
I'll be
get it.
able to.
You will get it.
Yes,
I'm
sir.
explaining it to you very well. This again is just like, this is the explicit expression for the Legendre polynomial. Now, this is what? This is Hamite polynomial. Hamite polynomial. Now, I'm going to the Legendre. I mean, Lagrange polynomial. Hamite. I finished with Hamite, and this is the general expression for Hamite. Now, let's go to the Lagrange polynomial. This is the expression for Lagrange. This is the polynomial. This is the expression. I mean, this is the equation,
Um,
and then this is the expression. This is the polynomial for it. Okay, just like in Legendre, we got his own equation, we got his own polynomial. Just like
yes,
illustrated, we got all of it. Bezel, we got it, we got its own expression. Where all these satisfy this. For the L is equal to 0, it will set the left hand side will be equal to the right hand side. L is equal to 1. If you get the expression, the left hand side will be equal to the right hand side. Just the same way we did for Bezel. The same thing. Bezel was J0, J1, J2. So this one to the legal polynomial is also expressed in this form. And this, I mean, the equation is this form, and the polynomial is this form. This polynomial satisfies this equation. Is that okay?
yes, sir.
Now, let's take for example now the Hamite polynomial calculation. Find the third order Hamites. This is the third order. Find H3. Remember, I just spoke about H1. We're able to do that one very quick. H2, H3. Now, look for the H3. For H3, we did for H1. H1 is going to give you this. If we go back there, we'll see that H0, we saw it was 1, right?
Yes, sir.
H1 too, if we use the polynomial, we're going to get 2x. But when we get to x, it is easy for us to get to x. But when we start to get the third, the fourth, it will become more complex. So we're going to use this kind of formula referred to as the recursive relation, which you must keep at the back of your head. This recursive formula is very straightforward to give you the Hamite polynomial very well. Is that okay? Instead to use
Yes,
this,
sir.
instead to use this, if we use 2, we carry out with 2, we're going to get our answer very easily, right? But then we can use this recurrent expression, this recursive relation to easily get it. When we talk about 0, you put 0 here. Okay. When we talk about 1, you put 1. When you talk about 2, you put 2. Okay. Are you with me? Joseph? Joseph,
So the network is not good. I can't hear you.
can you hear me now? Are
Hello,
you,
sir.
are you seeing the board?
Sir,
Are you seeing the board? Are you seeing what I'm doing?
I can't even hear you. The network is breaking, so I can't hear
Are you
you.
seeing what I'm doing?
I can't hear you. I can't see the screen. No, sir. Okay.
Can you see
I
now?
can see it now.
Okay. What I was trying to explain to you is that they have given you the value for the 0 and the 1. Are you with me? Are you with me? Are you with me?
Hello, sir.
Can you see me now?
Hello.
Can you see
The
it?
network is bad, sir. I can't hear you.
Can you see the screen?
No, sir. Ah,
Can you see the
network you
screen?
down.
Can you see the screen now?
No, sir. The network is even break. I can't hear you.
But I'm recording.
No.
I'm recording. Um. So what do we do now?
Ah, I can't hear you, sir.
But you can answer my question. Maybe that you're hearing me.
I
Can you
can't
hear
hear
me?
you. No, sir.
Okay. What we'll do is I'll continue teaching, and if I send the video, you see it fine. Okay. Since I'm recording,
Sir?
I can hear your
I
phone.
can't hear you, sir.
Can you see me now?
Oh. No, sir.
Yeah. I will just continue with the record, and then I'll send you the recording. You follow it from there. I just have few slides to conclude. Whether you're following or not following, you know what? I'll send you the video because I'm recording. Is that okay?
Okay, sir.
So to find the third order Hermite polynomial, we use the recursive relation. And this recursive relation is given in this form. So for the first recursive relation, for the first Hermite polynomial, when n is equal to 0, it is 1. When n is equal to 1, it is 2x. So we want to look for the case where n is equal to 3. So for us to do that, we have to calculate this. We have to start with n is equal to 2. When n is equal to 2,
Ah,
we put the value here, we put the value here, and we arrive at this. Why? Now, this value,
ah. So I'm really missing, no. I can't hear you. I'm
this value,
missing, no.
we already have it. So by the time we put everything, we're going to get 4x squared. Yeah, I don't know what to do. Can you hear me? Hello? Can you hear me? Hello? Hello?
Sir, I can't hear you. It's breaking, no.
Can you hear me now?
Just left.
Can you hear me?
Hello, sir.
Can you hear me?
I can hear you now.
Can you see the screen? Can you see the screen?
Yes.
Can you see the screen?
Ah, yes, sir.
You can see the screen.
Yes, sir.
Okay. If you can see the screen. Now, what to find for the H3? The H3, we have to first of all know for H1. Are you there?
Yes, sir.
We have to first of all know for H0 and H1. Then we follow this recursive relation. Okay? So for this recursive
Yes,
relation, we
sir.
already know for 0, we all know for 1. Let's look for 2. For us to look for 2, anywhere we see n, we put 2. So we have 2x. Then we have h2 minus 1. We are going to get 1. So we have this expression, right? Which is representing this when n is equal to 2, right?
Yes, sir.
Correct. Then this other one, when n is equal to 2, 2 minus 1 is 1. So we have this. And then this one, 2 minus 2 is 0. We have this, right? So we now make substitution.
Mm-hmm.
H of 1 is equal to what? 2x. And then h of 0 is equal to 1. So that's why we put here. Then when we do that, h of 1 is 2x minus h of 0 is 1. So that's why we arrive at this. Then this will give you 4x squared. Is that okay?
Yes, sir.
Therefore, we go again and do expression for H3. So anywhere you see n, you put 3. So if you put 3 here, you realize that 3 minus 2, 3 minus 1 is 2. Then this one will give you 2 into what? Um, this will be 2, right?
Yes,
3
sir.
minus this will give you 2. So we get 4. So at the end of the day, we already have expression for H2. Are you with me? So we'll now put the expression for H2. So when we put H2 here, then push H1, we're going to have this. So hence, we have gotten our expression for H3. Are you with me?
Yes, sir.
Now, don't worry, I'm about to close because I think you're not getting me now. The Dirac delta function is actually referred to as the distribution function. It satisfies the condition where you move from zero to, minus infinity to positive infinity. Okay, this is how Dirac, this is a function, any function. Okay, and then this is the Dirac notation. This function is saying that, are you with me?
Yes, sir.
F of this delta function is equal to f of a. Okay, now let
Yes,
me
sir.
just put it that way so that you look at it. Let's see how we can solve one problem. Given this problem, evaluate the integral to satisfy the Dirac delta function, the properties of Dirac delta function. Integrate this. How do I give you this type of problem? I will just say evaluate the property of delta function for f of x is equal to e minus x squared. So this is how you do it. Are you with me?
Yes, sir.
So how do we solve this type of problem? This is the problem I've given you. By shifting the property of the delta function, we'll be moving. How would should I be? I feel you are not following me.
The network is not really good. Hello, sir.
I'm there. I don't know whether you're following me.
Yes, the network is breaking, so I don't really hear some of those things you are saying.
Um, I don't know whether I should just stop the class here and tell you bye bye. Are you seeing what I'm doing?
Yes, sir.
Okay, what I'll do is you will go and learn. I'll send you this material. I'll stop the class here. I'll send this material. Read it. If you have problem, it just five. Is it 4 slides, which is very simple to understand. I will send it to you. If you have problem, you call me back and tell me to explain some few things to you. Okay?
Okay, sir.
Okay. Have good night.
All right. Thank you, sir.
Yeah.
Yes, sir.